Hello, everyone. Welcome to our session. Uh, this is going to be a part of DP 700 session. So let me share my screen and get started. Okay. Once again, hello, everyone. And let me do a couple of stuff. And welcome back. In this session, we are going to look at one of the most important building blocks of the Microsoft Fabric Lakehouse, data lake tables. Every table you create in Fabric Lakehouse is a data table, and that's not an optional choice you make. It's the default table format, and it's the reason a Lakehouse can behave so much like a relational database while still storing everything as files in one lake. Now, the good news is that you don't have to work directly with the Delta Lake APIs to get value out of the Fabric Lakehouse. Most of the interactive tools in Fabric hide that detail from you. But once you understand the metastore architecture underneath, and once you are familiar with some of the more specialized Delta operations, your ability to build advanced analytics solutions on Fabric expands enormously. So over the next few sections, we'll cover what data lake actually is and how to create data tables in several different ways, how to keep them fast through optimization and maintenance, how to query and modify them from Spark, and finally, how to use them with streaming data. So let's get started. Let's begin with the definition because everything else follows from it. Delta Lake is an open source storage layer for Spark that adds relational database semantics on top of data lake processing. That single sentence is doing a lot of work. So let's unpack it. A data lake on its own is just files in folders. It's cheap, it's flexible, and it scales, but it gives you none of the guarantees you take from granted in a database. There are no transactions, there is no schema enforcement. If a job fails halfway through writing, you are left with a partial, inconsistent result. Delta Lake closes that gap. By using Delta Lake, you can implement a lakehouse architecture that supports SQL-based data manipulation semantics in Spark, with support for transactions and schema enforcement. The result is an analytical data store that offers many of the advantages of a relational database system while keeping the flexibility of file storage in a Delta Lake. Tables in Microsoft Fabric, lakehouses are Delta tables. And you'll see that signified by the triangular Delta icon next to tables in the Lakehouse user interface. Let's start by getting underneath the surface, what a Delta table actually is on disk, and what the structure buys us. So, what is a delta table? Physically, delta tables are schema abstractions over data files that are stored in delta format. For each table, the lakehouse stores a folder, and inside that folder, there are two things worth knowing about. The first is a set of Parquet data files. Parquet is a columnar, compressed, open file format, and it's extremely common in data lake ingestion pipelines. One important property to remember is that Parquet files are immutable. You never edit one in place. Every update or delete results in new files being written. The second is a folder called underscore delta underscore log. That's where the transaction details are logged in JSON format. Every change to the table produces an entry in that log. That transaction log is the secret ingredient. It's what lets Delta Lake give us atomicity, consistency, isolation, and durability on top of plain files. And it's also what allows us to travel back to earlier versions of the data. Keep this two-part structure in mind because almost everything else we discussed today, optimization, vacuum, time, travel, streaming, comes back to it. Let's summarize the benefits of working with delta tables. There are four in particular that matter. First, relational tables that support querying and data modification. With Apache Spark, you can store data in delta tables that support CRUD operations: create, read, update, and delete. In other words, you can select, insert, update, and delete rows of data in the same way you would in a relational database system. That's genuinely unusual for a data lake. Second, support for ACID transactions. Relational databases are designed to support transactional modifications that provide atomicity. Transactions complete as a single unit of work. Consistency. Transactions leave the database in a consistent state. Isolation. In-process transactions can't interfere with one another. And durability. Once a transaction completes, its changes are persisted. Delta Lake brings that same transactional support to Spark by implementing a transaction log and enforcing serializable isolation for concurrent operations. Third is data versioning and time travel. Because all transactions are logged, you can track multiple versions of each table row. And you can use the time travel feature to retrieve a previous version of a row in a query. We'll see exactly how that works later on. And fourth, support for batch and streaming data. Most relational databases store static data. Spark, by contrast, has native support for streaming through the structured streaming API. And Delta Lake tables can act as both sinks and sources for streaming data. We'll spend the last section of this session on exactly that. There is a fifth benefit that deserves a slide of its own because it's the one that makes Delta Tapes a good citizen in a wider architecture. Standard formats and interoperability. The underlying data for Delta tables is stored in Parquet format, the same format that's commonly used in data lake ingestion pipelines everywhere. There is no proprietary container, no lock-in. Any engine can read Parquet, can read your data files. So on top of that, Microsoft Fabric gives every Lakehouse a SQL Analytics endpoint. That means the same delta tables you create and populate with Spark can be queried in SQL without copying or moving the data. So one copy of the data written once in an open format, readable by Spark, by SQL, by Power BI, and by external tools. That's the interoperability story. And it's a big part of why the Lakehouse pattern has become so popular. Now that we understand what a delta table is, let's look at how to create one. There are several routes, and the one you choose depends on whether you already have data and where you want that data to live. When a create a table in a Microsoft Fabric Lakehouse, a delta table is defined in the metastore for the Lakehouse. And the data for the table is stored in the underlying Parquet files. With most of the interactive tools in Fabric, the details of mapping that table definition in the metastore to the underlying files are abstracted away. But when you are working with Apache Spark in a lakehouse, you get much greater control over the creation and management of delta tables. And that's what we are going to explore. One of the easiest ways to create a delta table in Spark is simply to save a data frame in the delta format. Here we load a CSV file into a data frame. And then write that data frame out, specifying the delta format and table name. So note what happens as a result. The data for the table is saved in Parquet files. Okay, regardless of the format of the source file we loaded in the table storage area of the Lakehouse, along with the underscore delta underscore log folder containing the transaction logs. And the table is then listed in the tables folder for the Lakehouse in the Data Explorer pane. So one line of code gives us a fully functional queryable delta table. In the previous example, the data frame was saved as a managed table. That means the table definition in the metastore and the underlying data files are both managed by the Spark runtime for the Fabric Lakehouse. The important consequence is this. Deleting the table will also delete the underlying files from the table storage location. You can also just create tables as external tables. With an external table, the relational table definition in the metastore is mapped to an alternative file storage location. The files area of the lakehouse, for example, or a fully qualified path to some other storage account. In that case, the table definition is still created in the metastore. So the table appears in the table's user interface for the lakehouse, but the Parquet data files and the JSON log files live in the file storage location, and you'll see them in the files node of the Lakehouse Explorer pane. And critically, deleting an external table from the Lakehouse metastore doesn't delete the associated data files. The data survives the table. So that distinction matters a great deal in practice. Use managed tables when the lakehouse owns the data end to end. Use external tables when the data has an independent life, when it's shared with other systems, or when its life cycle shouldn't be tied to a table definition. Here is how you create an external table in code. It's the same save as table call we saw a moment ago, but this time we add a path parameter. In the first example, the path points to a folder in the file storage location for the lakehouse. The table definition is created in the metastore. So the table shows up under tables, but the Parquet data files and the JSON log files are written into files. In the second example, we have supplied a fully qualified path instead. That ABFSS URL points at a completely separate storage location. The pattern is identical. Only the destination changes. The key takeaway is that the table definition and the data storage location are two separate decisions. Spark lets you decouple them, and external tables are how you do it. It's very common to create a table from data you already hold in a data frame. But there are often scenarios where you want to create a table definition in the metastore that will be populated with data in some other way. There are multiple routes to that goal, and here are the three we'll walk through. The first is the Delta Table Builder API. This lets you write Spark code that creates a table from an explicit specification, a name, and a set of columns with their data types. The second is Spark SQL. If you are comfortable with SQL DDL, you can use a familiar create table statement and simply specify using Delta. And the third route is different in kind. Saving data in Delta format without creating a table definition in the metastore at all. That gives you Delta files on storage that you can later overlay with a table definition or process directly through the Delta Lake API. Let's take each of these in turn. The Delta Table Builder API enables you to write Spark code that creates a table based on your specifications. You can see the pattern here. We import from the delta.tables module, call deltatable.create, and pass in the Spark session, and then train a series of builder methods. Table name, okay, to name the table, and then add column for each column. Product ID, product name, category, and price. Finally, execute commits the definition. The result is a table registered in the metastore with a defined schema, but with no data in it yet. You would typically follow this with an insert, a merge, or a pipeline that loads the data. This approach is particularly useful when the schema is being generated programmatically. When column definitions come from configuration or from metadata elsewhere in your solution, because you're building the definition in Python rather than writing static SQL. The second route is the Spark SQL create table statement. On the left, we are creating a managed table called sales orders. We declare the columns and their types exactly as we would in any relational database, and then we add using delta, to tell Spark which format to use. That's the only unfamiliar part of the syntax. On the right, we create an external table instead by adding a location parameter. And notice something important here. We haven't declared any columns at all. When you create an external table this way, the schema of the table is determined by the Parquet files containing the data in the specified location. That behavior is genuinely useful. It's ideal when you want to create a table definition that references data already saved in Delta format, or when you are pointing at a folder where you expect to ingest data in Delta format going forward. So you define the table once, and the schema takes care of itself. So far, we have seen how to save a data frame as a Delta table, creating both the table schema in the metastore and the data files. And we have seen how to create a table definition on its own without saving any data. There is a third possibility, saving data in Delta format without creating a table definition in the metastore at all. This is useful when you want to persist the results of transformations in a file format that you can later overlay with a table definition or process directly using the Delta Lake API. The code is straightforward. We call save with a path. Rather than save as table with a name, the delta files are written in Parquet format to that path, and they include the underscore delta underscore log folder with the transaction log files. Those logs record any changes to the data, including updates made through external tables or through the Delta Lake API. You can also control write behavior with modes. Override mode replaces uh, the contents of an existing folder with the data in the data frame. Append mode adds rows from a data frame to what's already there. These two modes will become second nature very quickly in any real, you know, um, pipeline. Here is a small but very handy piece of behavior that easy to miss. If you use a technique we just saw, writing a data frame with save rather than save as table, but you point that right at the table's location in the Lakehouse, Microsoft Fabric applies an automatic table discovery capability. It notices the data folder and creates the corresponding table metadata in the metastore for you. In other words, the distinction between saving files and creating a table quietly disappears when you write into tables. The table simply appears. That's convenient, but it's also worth knowing about deliberately because it explains behavior that can otherwise look surprising. Tables appearing in your lakehouse that you don't remember creating explicitly. Creating tables is the easy part. Keeping them fast as they grow is where a bit of engineering judgment comes in. So let's talk about optimization and maintenance. Before we look at tools, let's understand the problem they solve. Spark is a parallel processing framework with data stored across one or more worker nodes. On top of that, as we have said, Parquet files are immutable. New files are written for every update and every delete. Put these two facts together and a pattern emerges. Over time, Spark ends up storing your data in a very large number of small files. This is known unglamorously as the small file problem. Why does it matter? Because every file carries overhead. The engine has to listen, open it, read its metadata, and close it. When you have thousands of tiny files, that overhead starts to dominate the actual work of reading data. Queries over large amounts of data can run slowly, or even fail to complete altogether. Delta Lake in Microsoft Fabric gives us several features to manage this, and we'll go through them one at a time. Here are the four features we'll cover. The first is optimize write, which acts at the moment data is written, reducing the number of files created in the first place. The second is optimize, a table maintenance operation that consolidates small Parquet files that already exist into fewer larger ones. The third one is reorder, an optimization applied to the Parquet files themselves that makes reads dramatically faster across the Fabric compute engines. And the fourth is vacuum, which removes all data files that are no longer referenced, reclaiming storage. Note how these divide up. The first two are about file size and count. The third one is about how data is laid out inside the files. And the fourth is about cleaning up history. Together, they cover write time, read time, and housekeeping. Let's start with Optimize Write. Optimize Write is a feature of Data Lake that reduces the number of files as they are written. Instead of writing many small files, it writes fewer, larger ones. That helps prevent the small files problem from arising in the first place and ensures that read performance isn't degraded as the table grows. The good news is that in Microsoft Fabric, Optimized Write is enabled by default. For most workloads, you'll simply benefit from it without doing anything. If you do need to change that behavior, you can enable or disable it at the Spark session level using spark.conf.set. So, as shown on here, so and you can read the current value back with spark.conf.get, which is useful habit when you are troubleshooting write performance. One thing worth mentioning, optimized writing, optimized write can also be set in table properties and for individual uh, write commands. So you have session level, table level, and command level control, depending on how granular you need to be. Next one is optimize. Where optimize write acts at write time, optimize is a table maintenance feature that works on files that already exist. It consolidates small Parquet files into fewer larger files. A very typical moment to run it is after loading a large table, after a big ingestion job, for example. The results are threefold. You end up with fewer, larger files. You get better compression because compression works more effectively over larger blocks of data. And you get more efficient data distribution across the worker nodes. To run it from the interface, go to Lakehouse Explorer. Actually, I'm going to demonstrate the lab tomorrow, and I will show it. We then After going to Lakehouse Explorer, we select the ellipsis menu beside the table name and choose Maintenance. Then select Run Optimize command. At this point, you can optionally select Apply V Order to maximize reading speeds in Fabric. And we'll talk about V Order on the very next slide. Finally, select Run Now. So it's a handful of clicks, and it's the kind of thing that's well worth scheduling as part of a regular maintenance routine on your busiest table. Sorry. Oh. Now let's talk about reorder, which is one of the more distinctive pieces of Fabric. When you run optimize, you can optionally run reorder, which is designed specifically for the Parquet file format in Fabric. Reorder enables lightning fast reads with in-memory-like data access times. It also improves cost efficiency because it reduces the network, disk, and CPU resources consumed during reads. Reorder is enabled by default in Microsoft Fabric, and is applied as data is being written. It does incur a small overhead, about 15%, which makes writes a little slower. But in return, it enables much faster reads from the Fabric compute engines, including Power BI, SQL, and Spark. So the gains aren't uniform across engines. In Microsoft Fabric, the Power BI and SQL engines use Microsoft Vertiscan technology, which takes full advantage of V-order optimization to speed up reads. Spark and other engines don't use Vertiscan, but they still benefit, typically around 10% faster reads and sometimes up to 50%. Under the hood, we order works by applying spatial sorting, row group distribution, dictionary encoding, and comprehension to the Parquet files. And importantly, it's 100% compliant with the open source Parquet format. So every Parquet engine can still read those files. You are not trading away interoperability. The one scenario where you should think twice is writing intensive workloads as staging data store, for instance, where data is only read once or twice. So there, the 15% write overhead may not pay for itself. And disabling reorder might reduce your overall ingestion processing time. The last of our four features is vacuum. And this one is about housekeeping. Remember the pattern. Every time an update or a delete is done, a new Parquet file is created and an entry is made in the transaction log. The old Parquet files are retained because that's what makes time travel possible. But it means Parquet files accumulate steadily over time, and that costs storage. The vacuum command removes those old Parquet data files, but this is important. It does not remove the transaction logs. Data files that aren't currently referenced in a transaction log and that are older than the specified retention period are permanently deleted when you run vacuum. The trade-off is direct. When you run vacuum, you can't time travel back earlier than the retention period. You are exchanging history for storage. So choose your retention period deliberately based on your data retention requirements, your data size, and storage costs. How frequently data changes, and any regulatory requirements you are subject to. The default retention period is 7 days. That's 168 hours. And the system prevents you from using a shorter one, precisely because shortening is a destructive decision. You can run vacuum in two ways. Through the interface, it's the same path as optimize. In Lakehouse Explorer, select the ellipsis menu beside the table name and choose maintenance. Then select run vacuum command using retention threshold. Set your retention threshold and select run now. Or you can run it as a SQL command in a notebook, as shown here. Vacuum the table name, right? The and retain followed by the number of hours. So that means you can run vacuum on an ad hoc basis or schedule it using Fabric notebooks as part of a routine maintenance job, which is what most production environments end up doing. One detail that's genuinely useful for auditing. Vacuum commits to the delta transaction log. So you can view previous runs using describe history on the table and see exactly when maintenance last happened. We'll come back to describe history shortly because it's also the gateway to time travel. The last topic in this section is partitioning, and it's a good example of an optimization that can help enormously or hurt badly depending on the situation. Delta Lake allows you to organize data into portions. That might improve performance by enabling data skipping. That's boosting performance by skipping over irrelevant data objects based on an object's metadata. Here is the classic example. Imagine large amounts of sales data. You could partition that sales data by year. The partitions are then stored in subfolders named year equals 2021, year equals 2022, and so on. If you only want to report on sales data for 2024, the partitions for all the other years can be skipped entirely. The engine never even opens those files. That's a dramatic improvement in performance. But not state conditions. Partitioning of small amounts of data can actually degrade performance because it increases the number of files and can exacerbate the small files problem we discussed earlier. So use partitioning when you have very large amounts of data and when the table can be split into a few large partials. Avoid it when data volumes are small, when the partitioning column has high cardinality, because that creates a huge number of tiny partitions or when the column would result in multiple nested levels. The rule of thumb is few and large, not many and small. With our tables created and tuned, let's turn to the day-to-day work, querying and modifying data in data tables from Spark. The most common way to work with data in data tables in Spark is to use Spark SQL, and there are two styles you'll see constantly. The first is embedding SQL statements inside another language, such as PySpark or Scala. By using the spark.sql library. In the example on the left, okay, um, so we are inserting a row into the products table by passing a SQL string to spark.sql. This is the style you want then. The SQL is being built dynamically or when it sits inside a larger Python function. The second style is the double% SQL magic. Put double% SQL at the top of a notebook cell, and then entire cell is treated as SQL. On the right, we are running an update statement to change a list price. This is the style you want for readable standalone SQL, and it's very natural for anyone coming from a database background. Both do the same thing against the same data table. Choose whichever fits the code around it. Sometimes you want to work with delta files directly rather than with catalog tables. When that's the case, it may be simpler to use the Delta Lake API. The pattern is create an instance of a Delta table from a folder location containing files in Delta format. Using Delta table dot for path and then use the API to modify the data. In this example, we point at a folder in files, okay? Create a delta table object and then call update on it. Update takes a condition here, rows where category equals accessories, and a set expression that reduces the price by 10%. Note what this gives you that plain SQL doesn't. You are working with a Python object, so conditions and expressions can be composed programmatically. And you are addressing a path, not a registered table name, which means this works perfectly well against Delta folders that were never registered in the metastore at all. Now, for one of the features people find most striking when they first meet it, time travel. So, modification made to Delta table are logged in the transaction log for the table. And because they're logged, we can use those logged transactions to view the history of changes made to the table and to retrieve older versions of the data. That's what time travel means here. To see the history of table, use the describe history SQL command as shown on here. The results shown the transactions that have been applied to the table, the operation, the timestamp, the version number, and more. For an external table, you specify folder location instead of the table name it quotes. Once you know which version you want, you retrieve it by reading the Delta file location into a data frame and specifying the version as an option. On this part, version as of 0 gives us the very first version of the table. Alternatively, you can specify a point in time with timestamp as of passing a date. Think about what this makes possible. Reproducing a report exactly as it looked last quarter. Debugging a pipeline by comparing before and after states. Recovering from a bad load without restoring a backup. All of it comes from the transaction log we met at the very beginning. Everything we have explored so far has been static data in files. Let's finish by looking at what happens when the data doesn't stop arriving. Many data analytics scenarios involve streaming data that must be processed in near real time. You might need to capture readings emitted by Internet of Things devices, for example, and store them in a table as they occur. The elegant thing about Spark is that it processes batch data and streaming data in the same way. That means streaming data can be processed in a real time using the same API you already, know. A typical stream processing solution involves three stages shown here. First, constantly reading a stream of data from a source. So second, optionally processing that data, selecting specific fields, aggregating and grouping values, or otherwise manipulating it. And third, writing the results to a thing. Spark supports this through Spark structured streaming and API based on the idea of boundless data frame, a data frame that never ends, into which streaming data is captured for processing. A structured streaming data frame can read from many kinds of streaming sources, network ports, real-time message brokering services such as Azure Event Hubs or Kafka, and file system locations, and as we are about to see, Delta tables. So where do Delta tables fit into a streaming solution? In both places. So you can use a Delta table as a source or as a sink for Spark structured streaming. As a sink, you could capture a stream of real-time data from an IoT device and read that stream directly to a Delta table. You can then query the table to see the latest stream data using exactly the same SQL you would use for any other table. As a source, you could read a Delta table as a stream, which enables near real-time reporting as new data is added to the table. And of course, you can chain them. Read from one delta table as a source, transform the stream, and write to another delta table as a sink. That's precisely the example we are going to walk through now. Let's build this end to end. First, we create a delta table to store details of internet sales orders underscore in with an order ID, a date, customer, and a quantity and a price. Nothing unusual. It's an ordinary delta table created with create table and using delta. A hypothetical data stream of internet orders is then inserted into that table and display the input table with a normal batch read to verify what's arrived. The interesting part is on the right. We load a streaming data frame from the delta table using Spark dot read stream, specifying the delta format and delta and data table this, sorry uh, delta format and the table name. Okay, you can check that the stream really is a stream using is streaming property, which should return true. Now, one important caveat. When using a delta table as a streaming source, only append operations can be included in the stream. Data modifications, updates and deletes can cause an error unless you specify the ignore changes or ignore deletes option. That's why ignore changes appears in this example. It's a small detail that will save you a confusing error message later. Once the data from the delta table is in a streaming data frame, you can use the Spark structured streaming API to process it. And this is where the same API for batch and streaming promise really pays off because the code looks exactly like ordinary data frame code. In this example, we are doing two things. First, filtering any rows with null in the price column are removed. Second, driving new columns is bike. So which uses instr, instr is one. Test whether the product name contains the word bike and casts the result to an integer. And total, which multiplies quantity by price and casts to decimal. You could go much further. Of course, a common pattern would be to count the number of orders placed every minute and send the aggregate results to a downstream process for near real-time visualization. The key point is that filter and with column behave here exactly as they would on a static data frame. You ought to know how to write this code. Finally, we write the transform stream out to a delta table our thing. We use write stream, specify the data format, provide a checkpoint location, and start the stream against an output table path in the tables area. After the streaming process starts, you can query the delta table to see what's in the output table. There may be a short delay before you can query it, so don't be alarmed if the first select comes back empty. In the results of that query, you would see that order 3005 has been excluded. uh, because it had null in the price column. And you would see the two columns were added during the transformation is bike and total. And please note the last line. When you are finished, stop the streaming data to avoid unnecessary processing costs using the stop method. A stream left running is a stream still consuming capacity. This is one of the most common sources of surprise consumption in Fabric Workspace, and it's entirely avoidable. One option is that last example deserves a moment of its own because it's the difference between a demo and production stream. The checkpoint location option is used to write a checkpoint file that tracks the state of the stream processing. It records what has already been read and processed. Why does that matter? Because streams fail, nodes restart, sessions time out, jobs get cancelled. Without a checkpoint, restarting a stream means either reprocessing everything from the beginning or silently losing data. With a checkpoint, the file enables you to recover from failure at exactly point where stream processing left off. So treat the checkpoint location as a required part of any streaming write, not an optional extra, and give each stream its own dedicated checkpoint folder. This brings us to the end of today's theoretical session about delta tables. Tomorrow I'm going to demonstrate the lab related to delta tables. So I would like to thank you. And let's recap what we have covered today. We started with what data lake is, an open source storage layer that adds a relational database semantics to Spark-based data lake processing, built on Parquet data files plus a JSON transaction log. We looked at the benefits that structure delivers, CRUD, support, CRUD support, ACID transactions, time travel, streaming, and open interoperability. We then created, actually, we are going to create the delta tables with several ways tomorrow, and we're going to spend time on keeping tables fast, optimize write, optimize reorder, vacuum. So thank you all very much for your time. Please do work through the lab that actually I'm going to demonstrate it tomorrow. And I see you in the next session. Subscribe to my YouTube channel and also my Meetup group. And I'm going to share the PDF format of today's session in the chat, YouTube chat box. So see you tomorrow.